Alrighty, go ahead and get started here. Thanks everybody for coming. HMI tips and tricks. So in this talk, we're gonna assume that you guys know Unreal Engine and maybe even know a few of the things we're gonna talk about, but hopefully a few of the things you don't know about and will help you elevate your projects, whether it's HMI or, to be honest, mobile as well. HMIs are often considered in Unreal just mobile games. So yeah, hopefully you guys get something out of it. What we're going to talk about today, so we kind of divided it into 4 parts. We have project organization and planning, getting up and running with your project in kind of a best practice way. And then we're going to dive into content and art, things you can do to maximize what you get out of your art in Unreal, making it look as absolute, like the absolute best that it possibly can. We'll go into that. Then we're going to talk about debugging memory leaks, how you can help you find issues in your code and in your projects, and then we'll have a Q&A at the end. So the team here, I'm Joe. I'm a technical product director for HMI at Epic, and then my team here, we have Sean, who's the senior technical designer on my team, works on a lot of the functionality, demos, and features that we're working on. And then we have Jürgen here, who's a lead programmer for ApiGear. We'll be talking about that as well. So project and organization, let's get started. So first thing I like to start with here is talk about install builds. So what is an install build? So you can clone the source of Unreal Engine from GitHub. You get the engine source, and then you can start working on it right away. But when you get that source, you have to build the engine. You compile the engine for whatever platform you're on, and then you get a binary, and then you start working in the engine. An install build basically pre-compiles the engine and then leaves it for you to then deploy. And then when you deploy it, you can compile your Unreal project code, and then your engine is already compiled. So this is similar to the type of engine you get off of the launcher. And in the automotive context, this is really important because automotive companies will have plugins that do all kinds of things, expose data that they get from the car, widget libraries, content plugins that have 3D avatars of the car, environments, all kinds of different things. And you want to reuse as much as possible across your different HMI projects. You have different car lines, you have different platforms, and all of those platforms and car lines can benefit from using the same plugins. And so when you have an install build that includes those plugins, you're essentially getting a custom pre-compiled engine that has those plugins available. And so that's a really great way of distributing your internal work throughout the company. And so you can have an Unreal project on top of that install build, which will have maybe slightly different configurations based on the platform that it's targeting, and can enable different content also. Maybe if it's a different vehicle or a different trim or whatever, you can enable that as well. And so on the right there, this is just a simple example of a script that you would run to generate an install build. And notice the part about the platforms there, that's describing the platforms that you want that editor to support. So if you're working on Mac and you're going to be compiling with Mac, you would have the Mac OS in there. Same with Android, excuse me. And then you would get your install build down there at the final directory. So yeah, that's install builds. So next I'll pass it to Sean and talk about pack files.
Hi everyone. So pack files are an essential component that helps streamline game assets and optimize performance. In other words, what are pack files? It's basically a compressed archive of game files and data, similar to a zip or RAR file. It's a package asset that contains cooked data, such as models, textures, animation, audio, blueprints. Why use pack files? Pack files can be chunked and dynamically loaded and unloaded at runtime. This helps offset resource allocations as well as deliver new content post-launch. When to use pack files? So we use pack files when we want to take control over what assets need to be included or loaded in package. And they're also useful when delivering DLC, like I said, post-launch, or pushing OTA over-the-air updates to your vehicle. In this demo here, I have a quick example of showing the pack files in action. On the right, I have a package build. And at runtime, I'm able to dynamically load and swap car assets through the use of two separate pack files. There's a car template and just a normal car file there. The assets are garbage collected and cleaned up from memory when unloaded. And when they're being loaded back in, they are being read from disk. And the content of the new pack file is registered within UE. And we're then able to spawn the car in the scene. So how do we generate pack files? So we generate pack files. It's fairly simple. We start by enabling pack and chunk loading in your project settings. Next, you create a primary asset label, which is derived from a data asset. You set the chunk ID of the pack file, and that chunk ID will be separated into different packs when the project gets built. Finally, you package the build, and then the pack files can be found under your content pack in the build directory. I just want to note that pack chunk 0 will contain the core game assets that did not get split into individual pack files, and generally you want to leave those alone. But with the other pack files that do get created, you can rename them and move them anywhere that will be later streamed into your pipeline. And now reading pack files. So reading leads to, which leads to reading pack files. Pack files are the native code is the code logic is native in UE and can be found in the iPlatform pack CPP file, where most of the required functions can be found in the F-platform file class. The only caveat is these functions are only accessible in C++. To make things a bit easier, especially for the non-coders who like to use the pack file feature, we have created a pack file reader plugin, which consists of wrapper code and helper functions that make getting up and running the pack files a bit easier. This is accessible in both C++ and Blueprints. You can check out the download or download it from the QR code there. If you download the QR code, there's a bit more documentation that gives a bit deeper dive into how the pack file system works. Next, I'm passing it to Jürgen, who's going to talk about ApiGear.
Thanks, great. So ApiGear is a way to shield your Unreal editor and your project from the underlying platform. It allows you, when you work with embedded hardware, to stay independent from the embedded hardware. We experience projects with large OEMs where they start happily making the first demo and then moved into projects, and then suddenly, slowly, hardware dependencies creeped in, or dependencies to external libraries which are not compatible with all operating systems where designers are working on. And ApiGear is a way to keep designers always productive, independent on the hardware. So software integration made easy in this sense. So software integration can be really hard. We have seen it with a lot of agencies which hire plenty of people, fresh people from universities. They create software. Everyone creates software in a different way. The software, the C++ code style, different qualities. Different teams have different needs with testing. And what happens there is that the designers at this time, they have to wait until the services are ready. And until they're ready, only then they can start using those data endpoints. But if you don't have a simulation at the end, which you can use on your desktop PC, then you suddenly get really depending on the hardware. And it's not really much fun to kind of open the door all the time on the car, trying to figure out that the CAN bus signal for the door open close arrives. Also, it's very late in the project that you have actually a car and you have a CAN bus in the first place. So to do this, or to shield us from this, we introduced a way to abstract ourselves from the platform. Also, what's very important is APIs are changing over time. And they have a different rhythm than, or the HMI-driven APIs have a different rhythm than the platform APIs. Like they cycle maybe every month, but you from your HMI team, you want to cycle much faster because you have a tool like Unreal Engine where you can move fast. And you would like to have data in a way which allows you to consume it easily into your HMI. And not like it comes from the platform team thought about, okay, probably you need to have this data. And they say, oh no, now I have to iterate to all of those data elements and extract one information because I only need this one information for displaying in the HMI. So for this, we want to drive APIs from the HMI way and then connect it, integrate it with the APIs which are coming from below, from the services. And there's always normally some kind of layer in between, which we call it's a double cake. You have double layer cake, you have HMI APIs or view models, and then you have the platform APIs. And then change always. And changing late in the production cycle, it's very expensive and very risky. So you need to make sure that the change is kind of implied or inside your whole process, how you develop software. Change will come, it's inevitable, embrace change, not kind of work against. So what API gets at the end, it's like you have an API definition file, which describes your API surface. And then we have a code generator, and then which generates, in this case, Unreal Engine plugins. What happens here is that we use in the code generator, we have a transformation library, which transforms the API definition into actual code. And the transformation library is written in a way that everyone can write their own templates. It's really like everyone can just easily adapt it to their needs because everyone has different needs for their platform. Some people prefer uppercase letters, some people prefer lowercase letters, some people prefer the class extends a different object because maybe you have a common object. Some people expect code should look differently. So all of this code is open source, so you can take it and adapt it to your needs. We have predefined templates which you can use, and they work. We maintain them, and they work perfectly. And other plugins can be extended. We currently have support for C++, for Unreal Engine C++. We have Python, TypeScript support, Go support, Java support, all of these templates. So it's like really cross-platform. We want to level the playing field. It should be as easy as integrating an Unreal Engine as it is with other technologies. That's very important. So let's create an IVI tuner. We are all in the automotive business, and we want to create the 50th IVI tuner. So tuner normally consists of a tuner where you can scan stations, you can have stations which are kind of discovered. You have favorites, you have a station in the first place. In the favorites, you can store a station, you can retrieve station, you can see the list of stations. So we have discovered, or we have created a very simple IDL. We have two versions of the IDL. One is like developer-friendly IDL. The other one is a tool-friendly IDL, where we plan to have like a design tool. So you can have like design your API, so the designer hasn't go out of his kind of comfort zone. He can stay like in his comfort zone of a design. So you have wave bands, you have stations, so you describe those elements. You have interface tuner. And with an interface, we really mean interface. We really foster clean code. We foster interface creation so that you program against interfaces, not against implementations. Like all this kind of thinking about great programming experience or great thinking of senior developers, it's baked into our templates. So that you only experience interfaces inside your Unreal Engine, and then you can change the implementation on runtime. So you can say, oh, I want to have a local implementation, or I want to have maybe a remote implementation which speaks with a service. That's something you can change on runtime in using our models. Here we can see like we grab an IVI tuner, this is our local, but we also have an IVI tuner over MQTT, for example, or an IVI tuner over WebSockets. So we can talk with another one, WebSocket. And then everything is reactive, which means if you call a function like scan stations, and this changes the list of stations, then this change is propagated back to the UI. So you only have to bind to the change signal and then take the data and update UI about this. These are kind of best practices which everyone should use, but often forgotten because it's like you are under high pressure, you have to push forward with your features, and here you get it automatically. You just have to describe the API surface, what I want to have, which behavior I want to have, and then you go. Moreover, what we discovered is that people would love to have a simulation server. So we are working on a simulation server where you can simulate the whole behavior and the data. So that you can independently create scenarios, maybe this open door, closed door every second, so that you can see in the UI how my animation really works. And this is independent of any implementation. So designers can start thinking day one. Think about an API which you want to consume in the UI, create a simulation server, and get going. And then wait until the backend people come back, the service people come back and provide the implementation. Additionally, we have API monitoring. So we record the API interactions. And you can see like what happens here. What happened on this API, which data came in and out. And so if I press a button, does the API really get called or not? Because often we get feedback, oh, the API or the UI doesn't work. I pressed the button and the door didn't open. How can it be? The UI is broken. Until you figure out most of the time, it's not the API which is broken, it's an underlying layer which is broken. Something hasn't reacted on the signal they received. This you can just discover with API monitoring. And you get, it's like analytics, but on an API level. So we created the IVI demo. It's a small demo. You can check it out. It's on github.com, ApiGear, very unusual, and IVI demo. So we are there. You will find a lab, very simple lab, a solution to the lab, and then a more complex IVI demo. We hope to expand on the IVI demo in the future to get more modules inside, so that we have a very nice abstraction layer below Unreal Engine, so that people can have a starting point to create their own integration into Unreal Engine. I think I hand over to Son.
Yeah. So I'm going to talk about content, performance, and optimization. And like Joe had mentioned earlier on, building for HMI is similar to building for mobile. We have to be pretty aware of the restraints that you have of the hardware you're working with. So some content performance tips. Number one, be aware of draw calls. Draw calls are the number of times the GPU is called to render, each time taking processing time in memory. So reducing the amount of draw calls will obviously be a big optimization in your project. Some of the ways to reduce draw calls is model optimizations. So combining meshes together, combining the material IDs or reducing the amount of material IDs that a mesh will have. Some other things are using instance meshes or hierarchical instance meshes. Utilizing LODs. Having a vertex complexity not be shown when you're distance in the screen is a big reduction. You can import your own LODs. If not, you can use the built-in LOD tools that Unreal supports. If animating objects with a lot of moving pieces, we recommend using skeletal meshes. So for example, if you have a car that is completely animated, the doors open, the trunk, the hood, the windows go down, and having these separate models inside a single blueprint would increase the amount of draw calls. So bringing that down into a single skeletal mesh would be the optimal solution for that. If needing fully transparent surfaces, mass material will always be cheaper than a translucent material. Also, be aware of texture size. And to properly nip down textures, use a power of 2, as well as consolidate textures. So reducing the size of textures. You don't need a 4K texture for everything. If you can get down with a lower res texture, it will reduce the memory and overall performance cost. Use channel packing, so pack textures together. Be aware of material complexity. You can use some of the viewport tools to see your material complexities inside the scene and adjust there. Check the asset impact. So you can use the size map to see the the size, the impact that an object has, and also the references that it has inside the scene. It's also, so it's the memory and it's the size on disk. And if you cook your asset, you can use the asset audit to get a very accurate representation of what it's doing. Render techniques. So we technically use 3 different render techniques: forward, deferred, and desktop rendering. Forward will be the fastest option for simple lighting setups, and it's generally the most commonly used things in HMI projects. The work is typically being calculated on a single base pass. Deferred rendering is useful in cases with scenes with big lighting scenarios. The work is being calculated on a separate base pass. And our desktop. So desktop is experimental. It's where we use the full rendering force of the Unreal Engine. The only caveat with that is it's higher performance at a higher cost, and generally will be next-gen hardware. So hardware that we see in automotive today typically won't use desktop rendering. Anti-aliasing techniques. So we have TAA, FXAA, and MSAA. Our Gen 4 TAA is the recommended for most use cases. It's scalable in a wide range of hardware specs. If you check out the temporal AA CPP file, you could see a lot of the different commands you can use to basically get the most out of that. The good thing about TAA is it gracefully handles sub-native render resolutions, meaning that if you go ahead and lower the screen percentage, it typically doesn't affect the scene that much. FXAA is a good alternative. It's a low-cost solution, low memory requirements, 0 temporal artifacts. And finally, MSAA is scalable. The only caveats with that is there's no support for deferred rendering, and it has a much higher cost at GPU and memory. So I'm going to go over some anti-aliasing comparisons. So you can see here at native resolution, we have a close-up of a car here. These are different just AA, the different AAs. You can see if you look at the panel gaps and around the side mirror here, you can see a lot of the aliasing happening. And you can see the difference between the two. So in my opinion, I think TAA wins out of these 4. So now we take the screen percentage and drop it down to 50. And you can see that TAA will still be the leading winner out of these 4 images here. So it's really just test out what you have, try all the aliasing, try all the render types, and basically whatever works best for your project. Some additional tips here is start the project with target with mobile platform. Doing so will disable most of the unsupported and generally overkill mobile features. Remove any unnecessary plugins. This will reduce package size and decrease build times. Start with medium scalability. Then you can add or subtract based on your project and hardware needs. And finally, profile early and often. So Unreal has many built-in tools, such as profile GPU and insights tracing, or you can look into external tools that decompose the frame, such as RenderDoc. And passing it to Joe for debugging memory.
All right, thank you. So memory leaks. So they can happen. We, like a lot of other things at Epic, rely on our tools to help us identify and find them quickly. And with with install builds and Sean saying profile often, you can actually automate being able to detect and track memory leaks, which is really cool. So we'll talk about that. Let's do something bad. So I have a leaked object here and a leaker, which is going to leak the leak object. It's going to spawn this leaked object every tick. In this example, it's just a regular shape, but if you had, say, a car or something, this could blow up very quickly. And then what we're going to do is when we run this, we're going to run down there on the command line memreport-full. We're going to wait a few seconds, let Unreal do its thing, and then run memreport-full again. And so what this does is it generates a memory report. -full will generate a full memory report. And memreport is a combination of different console commands to give you a complete picture of the memory that Unreal is using. And we're going to diff those. And I encourage you guys to run that command on all of your Unreal projects, if you haven't before. Get an idea of what they're doing and how the memory is being organized. I bet if you haven't done it, I bet you will be surprised at what you'll find in there. Because often you will have things in your project that you're like, I didn't put that there. And it'll help reduce your memory. But for the sake of this slide, I couldn't include the entire memreport, so I just got the chunks that were important. And so on the left side, you can see the first memreport, which, again, I was saying that a memreport is a combination of different commands. And so the first command there you see is object list dash resource size sort. And that resource size sort is very important because it's going to sort those objects based on how much resources they use. And so if you diff that against a later memreport, the diff will actually color the objects that are using a different amount of memory than they were in the first memory report. And so you actually get the leak, you can see on the right there, that the leaked object is actually highlighted green because it was sorted and it's in a different sort order on the right memory report. So this is a really, really great way of tracking down memory over time. And when we talk about using Unreal Engine in HMI, there's a lot of CI/CD and automated tests running. And automated tests have the ability to run these memreports. You can actually chart these things with automation and keep track of them over time. And so this is a really powerful way of finding what your Unreal Engine scene is doing in terms of memory. And while we're in here, just another part of the memreport dash full that's really important is this command list textures. This portion of the memreport shows all the textures that are used by the project, and it sorts them from most expensive to least expensive. And in new projects, if you were just open a brand new Unreal Engine project and just run it and run this, you usually see, I don't know if it's still true in 5.5, but in previous versions, you would see a bloom texture, which is 2K by 2K or 4K. And you'd see it at the top. And so that's a great candidate to remove if you don't use high-end bloom in your project. But it's a really great way of showing you what projects you're using or what textures you're using in your project. And then, as Sean was saying, channel packing is very important. And so when you combine this memreport of your textures with the channel packing strategy, it gives you not only a way to find the textures that are causing you memory issues, but maybe you can think of ways to eliminate textures entirely by packing them together. And so this is a really powerful way to find your texture, to do that. And now, so we also, in the state of automotive talk earlier, we mentioned single instance and multi-view. And these are plugins that kind of enable Unreal to be embedded into Android apps. And so in this case, you might have a good memreport here in Unreal Engine, but then you need to perhaps look into the API on the Android level and see what's going on there. For this, you can go into Android Studio and use the profiler there. And the profiler in Android Studio actually has like a label that tells you if you're actually having leaks on the Android level, and that's a very powerful tool. But generally, between memreport and between Android Studio, you should be able to find just about any memory leak in Unreal Engine. And I should say that there's kind of two places where memory leaks can occur in general. One is in the content or in the project, the UE project, where you do, like I showed, where you do the leaker and blueprint or some other thing, and then in the engine. And in general, engine memory leaks are extremely rare. So it's important to make sure that you check with due diligence your project first and use this strategy, and then you know, maybe in the off chance, you know, you might find a memory leak in some kind of engine feature, but those are generally addressed pretty quickly. So yeah, that's it for that. Well, thank you very much.
Thanks.
Thank you, guys.